Hi there. We are going to be talking about sedimentary rocks and soil and weathering. How do sedimentary rocks form? Well, first you have to have sediment. Sediment is loose material, particles of sand, clay, silt in a loose state, which are weathered, broken down from other rock, transported or eroded, then transported into a depositional environment. That is important. In order to get a sedimentary rock, you have to have a sediment traveling to a place where it can rest, get buried, get compacted, get cemented, and turn into sedimentary rock over time. For example, you might have a mountain or a cliff that gets attacked by wind, rain, water, gets weathered physically and chemically into a sediment, then it's transported to a low area, like a basin. It builds up into layers and becomes sedimentary rock eventually. So sedimentary rocks are extremely important to geologists. They form sort of a collection of pages in a book of Earth's history. We're looking here at a section of the Grand Canyon showing many layers of rock. This is all sedimentary rock. Sedimentary rock typically is seen as layered rock because it is laid down or deposited chiefly by water, but sometimes also by wind. So this shows sedimentary rock in layers. The bottom layer of rock is the oldest rock, and the top layer of rock is the youngest rock. So sedimentary rocks are valuable to geologists in many ways. They help geologists interpret the environment in which the sediments were laid down. For example, fine sediment that turns into claystone was deposited in a quiet water environment. Coarser sediment like sand may have been deposited in a surf zone off of a beach. Okay, and so if we look at the texture of the sediment that makes up the sedimentary rock, we can decide sort of what environment it was deposited in. Also very valuable, sedimentary rocks contain what we call fossils, which are the remains of organisms which lived in the past. The occurrence of fossils helps us classify past life, study past life, see the changes in past life from older rocks to younger rocks, and gives us a sense and an idea of relative time that has passed from, say, this layer that contains very old fossils to this layer which contains perhaps a totally different type of fossil which lived many years after fossils in this rock. Okay, so I mentioned weathering, and that's how particles of material get broken off from other material and form sediment. There's two types of weathering. There's physical weathering or mechanical weathering, and there's chemical weathering. Let's tackle physical weathering first. Physical weathering, as you might guess, takes place by brute force, by wind, by water, by organisms attacking rock, breaking it into little pieces. So here's a depiction of what mechanical weathering does. It takes a large block of rock, for example, and starts breaking it down. Now, the more a rock breaks down into smaller and smaller pieces, the more surface area is exposed. So this is a self-perpetuating process where if you have more surface area exposed, now you have more surface area that can be attacked by wind, water, and chemicals. So the more it breaks down, the more surface area is exposed, the more these processes of weathering can actually take place. When you have a rock mass, like you see up here, rock masses are, of course, as you know, stressed by tectonics, and the tectonics can form fractures in a rock mass. You can also get fractures in a rock mass through cooling of an igneous rock. So, as we've seen in the previous slide, this fracturing exposes more surface areas for water, chemicals, and so forth to attack these surfaces and form smaller and smaller blocks. As you can see here, what's happening is the rock surrounding or at the fractures starts to break down into finer particles, eventually into sand or even soil further down the line. This loose sandy material can be swept away, and you're left with this pattern of weathering, which shows that all the rock around this core stone has been weathered and transported away, forming this outcrop pattern that you see here in this actual granitic type rock. Another process of physical weathering is called frost wedging. This occurs only in cold climates or high elevations where, as you can see, you have a fractured rock mass. Water gets into this fractured rock mass through rainfall. In the cold temperatures of high elevations or cold regions, the water, of course, turns to ice. Now, what happens when water turns to ice? It actually increases in volume by about 9%. So the volume expands the volume of water into a volume of ice, which exerts a physical force on the sides of the fracture, wedging the rock apart. This kind of wedging can also occur through active organisms, such as a tree or a plant. A tree starts growing on top of a fractured rock outcrop. As its roots penetrate into and through the fractures, and the roots get bigger and bigger, they exert physical force, forcing the rock apart. As I mentioned, you can also get fractures in a rock mass through cooling. Here's an example of a basalt flow. I believe this is Giant's Causeway in Ireland. As this basalt lava flow cooled through time, it started contracting, and it's a fact of nature that as basalt flows cool and contract, they contract in this fashion, pulling away from each other into six-sided hexagonal columns, like a honeycomb pattern, more or less. It's quite an interesting phenomenon and something that's quite spectacular to see. Another physical weathering process is called exfoliation. This happens in igneous rock through cooling, fracturing through cooling, and also the relieving of pressure. You see this buried deep pluton, which of course is cooled granitic type rock, intrusive rock, which cooled underground. It's confined by overlying layers of rock. Now, as this rock gets eroded away, the rock underneath, the plutonic granitic rock, experiences a relief of a load. As it does so, it starts to expand from the relief of pressure. And as it expands, it forms layers or sheets that are more or less concentric, like the layers of an onion. And these layers can actually peel away from each other in sheets. So the act of peeling is called exfoliation. This happens to be in Yosemite. Here's the processes of physical and chemical weathering acting on a famous rock outcrop or cliff face in New Hampshire. It's actually even on the state seal of New Hampshire. It's called the Old Man on the Mountain. As you can see here, it's got sort of a profile that sort of looks like a rugged old man type profile. Many fractures. Well, it so happened that some years ago, this face gave way. The old man's face fell, if you will. Before that happened, there were measures taken to try to keep his face together by putting steel pins that you can see up here, also grouting or cementing the various fractures to keep it intact. Eventually, though, gravity was too much for this poor old man. His face just kind of slid away, so we don't have a face anymore. I don't know if they're going to rebuild it. Maybe hire the Disney company to rebuild the face. Who knows? See. These other set of weathering processes is called chemical weathering. As you might imagine, this is where chemicals attack surfaces like fractures, joints, faults in rock and start to break it down chemically. Typically, physical and mechanical and chemical weathering work in tandem, work at the same time. The more that physical weathering breaks down a rock, the more that chemical weathering can take place. So this first process of chemical weathering is called dissolution or dissolving. Happens to be a cube of sodium chloride, which is salt, composed of sodium ions and chlorine ions. As it's dipped into water, it starts to break apart. The oxygen ions in water molecule, H2O, are attracted to the positive sodium ions and surround the sodium ions. The negative chlorine ion is attracted to the positive hydrogen ion, and the water molecules surround this chlorine ion. So the water breaks apart salt by breaking up sodium and chlorine ions away from each other, and it's called dissolution or dissolving. This poor face of, I believe, a gravestone marker, used to be an angelic looking cherubic type face, no longer. This is the process of chemical weathering through acidic attack, acid pitting and weathering. So this doesn't mean that somebody threw a container of acid at this face. This means that through time, rainwater, which is slightly acidic, attacked this face over many, many years, started dissolving it through acidic attack. Rainwater contains, or the atmosphere contains carbon dioxide, and rainwater combines with carbon dioxide to form carbonic acid. That's the main culprit here. So if you're to be buried in a cemetery, hopefully many, many years in the future, it's best to get a granite headstone because granite doesn't dissolve as easily as limestone or marble does by attack from acidic rainwater. Here you can clearly read Mr. Peter Sweat's name, the year of his birth, the year of his death. No sweat. But the marble headstone here is basically illegible. You cannot read who this poor soul was and what the year of birth and death might have been. Taken to sort of a supercharged dissolving process, underground forms what we know of as a cavern. Limestone, of course, as you know, is calcium carbonate, which is subject to dissolving by water, which contains carbonic acid. So rain falls through the atmosphere, hits the ground, The ground is underlain by limestone, calcium carbonate. The carbonic acid in the rainwater penetrates through the ground and into this underlying limestone, starts dissolving it out. Eventually, all the limestone, or not all of it, but much of the limestone underwater, that's under groundwater, it's got carbonic acid in it, will start eating away at the limestone and form eventually these beautiful speleothems, we call them. A speleothem, S-P-E-L-E-O-T-H-E-M, is a formation caused by dissolving of limestone in an underground cavern setting. Now, the only reason we see this cavern is actually because the groundwater has drained away and gone somewhere else, leaving the remnants of limestone that have not quite been dissolved. Another process of chemical weathering is called oxidation. Oxidation is basically rusting. So you see these barrels made of steel. Steel has iron in it. The iron turns to iron oxide, which is the ingredient of rust. Eventually, many, many years from now, these barrels will become just piles of reddish orange iron oxide. Okay, so the ultimate or end result of physical and chemical weathering of sediment may be to turn material, original rock material, into what we call soil. Soil, of course, is extremely critically important to us. We grow plants in soil, trees, various types of plants thrive on the nutrients they can derive from soil. And of course, most of our homes are built on soil in valley areas. There are some homes built on rocks, but most houses, I would wager, are actually built on soil. So what is soil? Well, soil is this. It's made of mineral matter, it's made of air, it's made of water, and it's made of organic matter. That's a true soil. It's not just dirt. It's got all these ingredients in it. A good agricultural soil will have some amount of void space that's occupied by air so that gases can be exchanged freely, which carry nutrients back and forth from water to air and vice versa. Organic matter gives it that ability to absorb water and also contains important nutrients. A soil can develop into what we call a soil profile. If you were to go out to somebody's farmland and dig a trench, you might see layering that looks sort of like this. So let's start from the bottom. The bottom is bedrock, unweathered parent material. That's what it means, bedrock. As physical and chemical weathering occur, this bedrock starts to turn into broken down sediment. Okay, that's called the sea horizon. So it's partially altered parent material. Now let's switch our thinking to looking at it from the top to the bottom. The very top layer of a very well-developed soil profile is called the O horizon. O for organic. So it contains loose and partly decayed organic matter, such as leaves, twigs, roots, pieces of dead organisms, snail shells, so forth. And below that is the A horizon, which is mineral matter, so actual particles of sand, silt, and clay mixed with some humus, not humus, humus. Humus is organic material. So again, this is a rich layer of soil of minerals and organic material. This is the so-called active zone where roots of plants and trees get their nutrients from chemicals and from organic materials. and also is the zone in which little beasties like earthworms, snails, gophers, etc. do their activity to keep the soil well mixed and well aerated. Below the A horizon is what we call the E horizon, E for eluviation, which means, eluviation means it's a layer where mineral matter, fine particulates, and some chemical compounds are driven downwards by water movement and sort of transport through this layer. So this is an area of leaching where water is carrying various minerals continuously downward into the B horizon, where a lot of these minerals settle in and form a layer of very fine material, which forms a clay layer called the B horizon. Okay, so this is a generalized soil profile. If you go from region to region, there will be variations in the soil profile. If you go to a very dry desert region, you might have only parent material and a C horizon with very little organic material. If you go to a tropical forest, you might have an O and an A horizon that's 10, 15 feet thick, because there's so much organic activity, so much rainwater, so much chemical decay. Okay, so soil profiles vary according to regions in which they form, and also vary according to what the parent material is. Now that you understand sediment a bit better, let's talk about sedimentary rocks. This should look familiar to you. This is the rock cycle, the cycle in geology in which one type of rock can turn into any other type of rock. Let's concentrate on the bottom here. It has to do with sediment and sedimentary rock. So the, let's say an igneous rock can be attacked by physical chemical weathering, turns into sediment, gets deposited in a lake, let's say, as sediment. Then it undergoes the process of lithification. Lithification includes the transformation of sediment into sedimentary rock by burial, by compaction. As more sediment is piled on top of the sediment below, it packs that sediment down into a thinner but denser layer. Then, because there's a lot of water in between the voids of the particles of sediment, this water carries cement with it, calcium carbonate or silica, that through time will eventually cement particles together. So you have burial, compaction, cementation, and the turning of sediment into sedimentary rock. So let's look at the process a little bit closer. Take a look at this picture. Here you have a mountain range. Chemical and mechanical weathering break down the rock. So you can get rain helping here. You can get rivers taking particles of sediment and transporting them. You can have ice also taking particles of rock, transporting them. A glacier is actually a body of ice formed from compaction of snow that cuts, scrapes, transports many, many tons of rock and sediment downwards. So it's an erosional agent. A glacier is an erosional agent that takes weathered material and transports it. So is a river, so is a stream. And as we get further downstream, if you will, the river and the ice start to deposit these sediments. Deposition occurs when the solid particles settle out. Then you get perhaps most, if not all, the sediment ends up in the ocean, where it's deposited on the seafloor has many, many layers of sediment, which may be tens to hundreds of feet in thickness, to be buried and transformed into sedimentary rock. Let's talk about different types of sedimentary rock. The first type is called detrital. Detritus is a word that means fragments, so it stands to reason that one type of sedimentary rock would be a detrital rock. So a detrital rock is a sedimentary rock made of pieces. What are the pieces? Well, you have clay, you have silt, you have sand, all the way to boulder. So a clay is a size classification. A clay is, the size of a clay particle is less than 1/256th of a millimeter. Tiny, tiny, tiny. You can't see something that small unless you have a microscope. And the next biggest is silt and then sand. So a clay becomes a sedimentary rock called a claystone, which isn't shown here. A silt can become a siltstone. Sand, if buried, compacted and cemented, becomes a sandstone. A cobbly or coarse-grained type of sediment can become cemented into a conglomerate or a breccia. Let's look at examples of these different types of rocks. Here's a sandstone composed of cemented particles of sand. Simple enough. These orangey colors are chemical oxidation of certain iron minerals that are in the rock itself. Here's a conglomerate. A conglomerate, also called in England a pudding stone. You might imagine why. It's got bigger, coarser particles embedded in a finer matrix. So you'd find this type of rock originating from sediment that's deposited in, say, a river. River takes material, sorts it into finer grains and larger grains, transports all this stuff, and then if it hits a slowdown, a bend, or a leveling of the gradient of the stream, if the current slows down, it'll start dropping pebbles to form a gravel bar, for example. The gravel bar can turn over time into a cemented, buried, and compacted conglomerate. Different type of sedimentary rock would be a chemical rock. As you might imagine, a chemical rock is a rock made primarily from chemical processes. So here's a special type of chemical sedimentary rock we call an evaporite. An evaporite is formed from evaporation. This is Utah, the Bonneville Salt Flats. This is a desert region. Now the desert doesn't have a lot of water, but it does have water. Water flows from the surrounding mountains, carrying many minerals with it, dissolved within it, reaches this flat area and evaporates because of the desert heat. The water leaves, the salt stays behind. So what you have is a buildup of salt deposits, calcium, sodium chloride, also calcium chloride, borax, and other types of evaporites to form these deposits, which can build up over time into quite thick deposits. We've already talked about caverns. This is the Wind Cave National Park in South Dakota. We'll talk more about caves when we talk about groundwater, but these, as you might know already, little straws or projections hanging from the ceiling are called stalactites. These columns, these speleothems coming from the floor of the cavern are called stalagmites. This is from, of course, dissolution of calcium carbonate, calcite, by acidic rainwater and groundwater. Biochemical rocks are a combination of chemical process and biologic or organic activity. Here you see a coral reef. A coral reef is a geologic structure formed from the activity of organisms called coral polyp type organisms. So a reef is sort of a remnant of living creatures. The little creatures excrete calcium carbonate by taking carbon, calcium, and oxygen from the seawater to eventually build up reefs like you see here. And through time, creatures die, more creatures come in, build more reefs, they build up to many tens of feet of thickness sometimes to form these quite extensive structures. The Great Barrier Reef off the east coast of Australia, for example, is many hundreds of miles long and many tens of feet thick. Coquina. Coquina is also called shell hash. So what is this stuff? This is not a cornflake. These are bits or fragments, pieces of shells. Pieces of shells. Where would you find pieces of shells? What sort of environment? Well, if you walk down to the beach, near the water's edge, you might see fragments of shell washing in and out on the beach. Why did they get there? Well, perhaps these shells were tossed around by surf, by waves, and broken up into pieces, deposited in layers primarily of shell, and then buried, compacted, and cemented into this rock that we call coquina. This type of biochemical rock is called chalk. Chalk is composed of the remnants of millions, billions, perhaps trillions of tiny organisms which secrete a calcium carbonate shell, die and fall to the bottom of the ocean where they build up over many, many millions of years and are raised up, in this case, off the coast of Dover, England, by sea floor uplift tectonics. And we see exposed here these beautiful layers of biochemical rock that we call chalk. This is not ice, this is chalk. Another type of biochemical rock is called chert. Chert, as you might guess, is sort of similar to, remember obsidian? Obsidian's that volcanic rock, it's very glassy. Chert is pretty similar. It's actually made of silica as well, but it's silica released and created by organisms which secrete and build shells not made of calcium carbonate, but shells made of silica. These silica shells, again, build up in layers of the sea bottom and become layers of chert, which through compaction, burial, and cementation become quite hard and dense sedimentary rock that can then be shaped, chipped, and flaked into arrowheads, spear points, etc. Here's another category of sedimentary rocks, organic rocks. When we talk about organic rocks, of course, we refer to rocks that are built, made of organisms, and we primarily mean coal. Coal is not the same as petroleum. It's a rock that's made of the remains of vegetation primarily. If you have a swampy environment where you have a profusion of plants, water-loving plants, trees, various types of plants, they, of course, have a lifetime. They die, they decay, and they form a mat of organic rich material that we call peat. That's under very low pressure near the surface. Peat is a spongy, organic rich material, which can actually be cut and used to provide fuel and energy. People certain portions of Ireland, for example, cut this material out, and Scotland as well, cut this material out and can burn it in their stoves and fireplaces. Okay. Through burial and increased pressure compaction, this peat can become a material we call lignite. Now, lignite is a form of coal. It can also be burned to provide energy, light, and heat, but it doesn't have a real high concentration of carbon in it. That comes with greater burial, more time, more compaction, more densification into a coal that we call bituminous coal. So here's peat up here, here's the lignite, here's bituminous coal. The densest, most pressurized, if you will, most compacted type of coal comes from not only burial, but the forces of metamorphism, which really squeeze and stress this material into a dense coal that we call anthracite. Anthracite has the most packed together carbon of all the coals, so it's got the most carbon per unit volume and unit weight, and as you might imagine, it then provides the most energy per unit weight or unit volume. So it's the most intensely burning type of coal. We call that anthracite. Now, I mentioned before that sedimentary rocks help geologists recognize the environments in which deposition takes place. And some other clues besides fossils and grain size, texture, it's what we call a sedimentary structure, sedimentary structures. So if we look at this slide, this is the Navajo sandstone in Zion National Park, Utah. By the way, if you haven't visited there, highly recommend it. It's an astounding, beautiful place, part of the Colorado Plateau, which is full of wonders. Look at these lines in this rock. This is all sandstone. These lines represent the faces of sand dunes. So these are actually, if you will, petrified sand dunes. This was a desert environment for many, many years prior to today. The sand came blowing, for example, from the left to the right. The sand slipped over this face, slipped over this face. The sand dune built towards the right. So what you see here is a cross-section of the piling up of sand on the leeward face of a sand dune as the wind is blowing. Eventually these sand dunes became buried, compacted, and cemented into sandstone that you see here today. This is another sedimentary structure that we call a ripple mark. So a ripple mark, as you might guess, is something formed by a moving current, either of water or air. You can get ripple marks on sand in a desert, but mainly the ripple marks that are formed by moving water are usually better preserved. So if you visualize a shallow lake or pond with a sandy bottom, and you have wind-driven waves on top of the water that also move the water near the bottom. The water near the bottom moves the sand and puts little ripples in it. The sand then gets buried, compacted, and cemented into sandstone, which we see here, and the ripple marks on the sandy bottom caused by currents are also preserved. Another type of sedimentary structure, which would be great if you were lucky enough to discover new ones, are dinosaur tracks. So dinosaur tracks are considered sedimentary structures, or if you will, any kind of track left by any kind of animal. This large dinosaur was walking along a sandy, muddy bottom, leaving his footprints This looks like a smaller dinosaur which really doesn't know what to do. So this gives us a hint of not only environment, a possible muddy or wet lakeshore. The tells us that there was a dinosaur-like creature that lived here some time ago and left these footprints. Okay. Okay. Now let's talk a little bit more about how sediment gets from one place to another through the process of erosion. Erosion removes sediment, transports it to somewhere else. How? Well, by flooding is one way. In 1998, there was a hugely destructive hurricane called Hurricane Mitch in Central America. Every time you have a hurricane, you have what? Heavy rain. Heavy rain fills up streams. Streams start to flood, overtop their banks, remove material. You get a stream that looks like this. It's very brown or light brown in color because it contains a lot of moving sediment. Okay. In a desert environment, you also get erosion. Now, there's not as much water typically in a desert environment as there is in a tropical environment, but there is some. But there's also a lot of wind. Wind can shape rocks, can cut rocks, can sandblast rocks. So this rock formation is called a yardang. This is formed when wind carrying sand, say only a few feet above ground surface, at high velocity and over a long period of time. Desert winds can be very consistent, very persistent, and actually stripped away or sandblasted the softer rock, leaving the harder rock on top and eroding away the softer rock. So we have erosion from water. We have erosion from wind. When we have extensive erosion from wind, we can often see it from satellites. This is windborne dust blowing off the Sahara Desert all the way across the Mediterranean over the island of Corsica, I believe that's correct, I hope, and over the peninsula of Italy. Okay, so we're going to switch gears a little bit. We're going to talk about the processes of mass wasting, landsliding, slope failure. This has to do with sedimentary rocks having planes of weakness or that are sheared up because of faulting and cause movement of material on a hillside, which eventually through gravity and water can cause damage and destruction as this material moves down. You have landslides also in volcanic terrains because you can have a lava layer sitting on top of a weak rock that will eventually fail and cause the whole mountainside to come down. The hydrologic cycle is a representation of how rock cycles through various processes. It includes the rock cycle that forms igneous rock. It includes the hydrologic and rock cycle that forms precipitation, weathering, and sedimentation. But let's not dwell on this too much, but you can review this at your leisure. The Grand Canyon, again, is a stack of sedimentary rocks and volcanic rocks. Actually, the lowest rocks are what we call a schist, which is a metamorphic rock, which we haven't talked about yet. The metamorphic rock is a rock that's been transformed by pressure and heat. But the point of showing you this now is that you have the entire canyon was formed by erosion by running water, and you have these very steep slopes which occasionally fail through mass wasting, where a big block of rock just comes tumbling down or sliding down these slopes. So what causes soil or sediment or rock to move? You have a stable slope on the left where you have dry soil, interlocking grains. What happens if you introduce water to this slope? Well, the water penetrates into the voids between grains, starts separating the grains, so that now you have an unstable slope which is mobilized by water, so that the material now moves down slope. Here's an extreme example of a very rapid mass wasting process where you have blocks of rock falling. This is rock, of course, it's already been fractured. So the fractures represent planes of weakness. You get perhaps freeze-thaw, wedging the rock apart. Perhaps you get heavy rainfall, and the rock comes tumbling down onto a roadway, Highway 140. The only way to get rid of this rock, of course, is by blasting it away. Here's another example of a slope failure where you have tilted sedimentary layers, tilting this way from up to down this way. The clay bed is a plane of weakness. When they built a dam here, this created a lake. The lake saturated the clay bed and made it weaker. And all this sandstone on top of the weak clay bed then slid into the reservoir. This is called the Gros Ventre landslide. This is the scar that's left by the landslide in 1925. It entered the lake and caused overtopping of the dam and much damage downstream. Here in California, we have many of these types of failures. It's called a debris flow. A debris flow is caused by a collection of loose material in a very steep canyon. And we do get a lot of rainfall during some of our winters that saturates this loose material in a very steep canyon, and then it goes. These can be very fast moving. They can be quite dangerous. They can be injurious to life and property. And in a winter with heavy, intense rainfalls that we occasionally get here in Southern California, they can cause a lot of damage, as you'll see here in the community of La Conchita, a coastal community. In 1995, you had a massive failure of the hill. This is all very weak, not well consolidated rock. Then 10 years later, it failed again. So a number of people died from these failures. Okay, this is serious stuff. In 2005, I think 4 people were killed. Up to 8 or 9 homes were damaged or destroyed. Another type of slope failure is called a slump. This is a slump at Point Fermin. So again, we have weak materials. We have the introduction of moisture, and we have a sort of a downward motion at the upper blocks. That's where the slumping takes place. And as moisture migrates from the top through the middle towards the bottom, it forms a very wet mass of earth that we call an earth flow. So slump, earth flow. Slump, earth flow. But what's happening here is that we have an additional factor of the ocean coming in and undercutting these blocks and really making it unstable. This is a kind of mass wasting slope movement that's not fast, not typically real dangerous, and it's called a creep. Soil creep occurs on any and every hillside, but you won't see it happening because it's quite slow. But it can be damaging. If it continues to progress without being stopped, it can tilt or knock over walls, it can tilt fences, it can tilt gravestones, it can cause trees to grow curved rather than straight. So that means the upper layer of soil or weathered rock moves constantly down slope, Here you see it's even bending forward these tilted sedimentary beds. It can, again, knock over a wall, can damage roads. So if I was to try to mitigate this situation and repair the damage in the road, how would I do it? Well, the best way from an engineering point of view is to scoop out the unstable material all the way through the creep zone into firmer bedrock, take out this wall, so gouge this out, take out this wall, replace it with engineered, strong, compacted fill, rebuild this wall with some drainage behind it, and take out some of this loosey goosey, creepy soil and replace it with stronger stuff to maybe 10, 15 feet behind the wall.